Hi everyone, welcome to today's class. This is my topic number 11, and for topic number 11 I have again chosen a topic from chemical thermodynamics. This is a very important chapter for from the physical chemistry for CSIR-NET chemical sciences. That's why I am uploading again and again back-to-back videos from this chapter. And previously, I have uploaded two videos from chemical thermodynamics. One was the basics of thermodynamics and the zeroth and first law of thermodynamics, and other one has the heat capacity and the all the work formulas. Okay, which are very important for the exam point of view. And now I will be teaching you the degree of freedom and the equipartition theorem, which is also a very important topic. Some of you have heard about this topic, but the knowledge of this topic is very important to solve the questions from adiabatic process, and also some questions are direct questions are also from this topic. So let's start with today's topic, and rest you will understand. And I welcome everyone, and please make sure you have a pen and paper. And in this lecture only, we will solve various questions. So I want you to participate in that. You should also practice with me because our purpose is same, right? So our target is June CSIR-NET. Okay. So let's start with today's topic. So first, we will know about what is degree of freedom. So this term is actually familiar to you, right? If you can recall, then it will be good. But if you don't, I will make you recall the topic that it is the number of independent variables. This is very important. Independent variables that can vary in a sample or a set of data. So it is nothing but independent variables that a system can have. So we can change the variables, and it defines a system. Okay. So it can be calculated by considering the molecular motion. Calculated means, so for a particular, let's say, particular molecule or particular system, there will be some degree of freedom for that particular degree of freedom, which we can calculate. Okay, by considering the molecular motions. We can calculate the value of, so why we are reading this? Now question will come. I have previously also told you, just don't read like that. Okay, this is important for exam. Let's read it. That is fine, but you have to also understand that why we are reading this. So these are the some basic way to gain your interest. Okay, for a specific topic. So why we are reading this? So in the previous lecture, I have talked about that internal, in the previous and the first lecture also of thermodynamics, I have talked about the internal energy, right? U. Okay. And also in the previous lecture, the specific heat capacity, Cp and Cv. You all know now, right? So how we can calculate this? That is the concern, because we know Cp by Cv is actually gamma, and for adiabatic process Cv to the power gamma equal to constant, which we frequently use. Okay, so we want the gamma value for various type of gaseous molecules. Okay, to know the gamma value we have to have the idea about Cp and Cv, right? And we know the other relations, like here I am writing. So we know the other relations, like Cp minus Cv equal to R for 1 mole. Okay. So if we know any of these values, we can calculate the other one, right? Because this is known quantity, this is constant, gas constant. So Now I am coming to the CV. So CV du equal to CVDT. This is also an important formula. These formulas actually you should not forget. Okay. So this is CVDT. Okay. So from this, so now coming to the see how the relations actually we can find that from degree of freedom. So why I am telling this all, because from degree of freedom we can calculate. So we can calculate degree of freedom by considering molecular motions. Fine, one point clear. Second point is, by calculating the degree of freedom, we can calculate the internal energy of a system or of a molecule. Okay, fine. So we know DOF, tick. We know now, sorry, not DU, I will say U. Okay. So we know now U, internal energy. So, okay, fine. Yes, internal energy is very important thing, okay, for the system. To know is it is a very important thing to know about the system. Fine. But now what we can do further? So using the U, we can actually apply this formula to calculate CV. Du equal to CVDT, this formula. So now we know CV also. What can we do now? So we can put the value of CV here and calculate the CP. Okay. Now we know the CP also. So we know DOF, we know U, we know CV value, we know CP value, right? Now we can calculate the gamma value also. So see how much important this topic is. So please patiently you will watch the video and you will understand all the things. Okay, how to calculate and everything. So firstly, the motion is the movement of a constituent particles of or molecules. Let's say a system is there. So motion is actually, what is motion? Why we are reading motion? Because by molecular motion we can calculate the degree of freedom. Fine. So motion is the movement of constituents, particles and molecules. This is simple. So molecular motion can be three types: translational motion, rotational motion and vibrational motion. So what is a translational motion? You have to have some idea, right? So you will be going some interview and you can be asked these kind of questions. And also for your interest, own interest also, you should know about this thing. So translational motion is when particle is moving to one axis. So let's say this is x axis. Okay, so particle can move along this, right? This movement of particles along a axis is called translational motion. Okay, movement of a particle or atom or anything along one axis. Fine. Rotational motion. What is rotation? We know rotation, right? If this is a molecule, rotation is like this. Fine. So rotational motion also we know. Fine. So we know now rotational motion. Now vibrational motion. Vibrational motion can be through a bond. We can say if bond is present through the bond, and it can happen both ways, like this and this. Okay. So just like that, you can consider a spring. Spring is vibrating if you just stretch it and leave it. Okay. So vibrating, right? So vibrational motion is like that. So double motion. Fine. So you know three kind of motions are there. Fine. If a molecule has, now we are reading. So we were studying motion. That is fine. Now a different thing. if a molecule has n number of atoms, if a molecule, this is not depending on the motion. Why we are reading motion, that I'll come to the next slide. So here only, if a molecule has n number of atoms, then total degree of freedom of that molecule will be 3n, where n is number of atoms. For example, let's say for H2, okay, n equal to 2, obviously 2 H atoms. Now total DOF will be 3 into 2, 6. And for CO2, again n equal to 3, and total DOF will be 3 into 3, 9. Fine, we know now total DOF. Okay, fine. But we want to know that due to this kind of motion, actually, how much DOF is involved. Okay, this is the total DOF. But we have different contributions in the U, calculating the internal energy. So we have different contributions of translational, rotational and vibrational motion. So that's why we have to first know that what is the degree of freedom associated with translational motion. Okay, so for linear molecule can be linear or non-linear, right? Let's say CO2 and SO2. CO2 is linear but SO2 is not, as it has lone pair. Okay. So now for linear molecule, translational motion is 3. For rotational motion is also 3. Vibrational motion is 3n minus 2. Okay, I think here I have done some mistake. Yes, this will be clear. Okay. So for translational motion, for linear molecule, linear or non-linear, always translational motion will be through x, y and z axis. That's why actually translational motion is consisting of the 3 DOF. And rotational, for linear case it is 2 and for non-linear case 3. Fine. So how much is left now? So total is 3n. So it will be 3n minus 5 because 3 plus 2 is 5. So total of this will be 3n, right? So 3n minus 5 will be vibrational motion. And here, as it has 3, rotational motion has 3 degree of freedom. So here it will be 3n minus 6. Fine. Now equipartition theorem. It is very important. So it relates the temperature of a system to its average energy, or we can say internal energy. Okay. So what is it works? It relates the temperature of a system to its energy. So by knowing the temperature, you can have the idea that how much energy that system consists. Okay. It states that the total energy of a system is equally divided into all DOFs. DOF means degree of freedom. So it states that total energy of a system is equally divided into all DOFs. Fine. The contribution of energy made by each DOF each. So we know equally divided, that is fine. And we can calculate the DOF also. In the previous slide, you know now, but only we have to know that how much atoms the molecule has. Okay. Now the contribution of energy made by each DOF is kT by 2 for one molecule and RT by 2 for 1 mole. Okay. K is here Boltzmann constant and R is the gas constant. Okay. So so we know, right, Boltzmann constant, this one, R by N. Okay. So what we learned here, so we know now each DOF which we talked about, the DOF consists of kT by 2 or RT by 2 energy. Okay. So now we can calculate the energy associated for a system. Okay, see how? First, we have to know, okay, we have to first summarize the all the things which we have read just now. Okay, so first we know for linear, translational motion is 3, rotational is again 2, 2 and vibrational is 3 and minus 5. For non-linear it is 3 again, it is 3 and it is 3 and minus 6. So this is 2. Please note it down, this is 2. Now again the contribution for each DOA. Okay, R by 2 because okay, no, RT by 2 will be there. If here CV will be written, then R by 2 will be there. But here will be RT by 2. It will be RT by 2 and here also it will be RT by 2. Okay, but here it is R. For vibrational it is R. But here another twist is there. For high temperature we can consider R. For high temperature we can consider the contribution uh, of vibrational motion towards the U, calculating the U. Okay, but at low temperature the contribution is 0. Okay, so in the next slide the important thing we will read again that vibrational DOF is temperature dependent. Okay, so if in the question something is asked in a tricky manner, you should always remember that whenever temperature dependent thing is there, that means it is associated with vibration. And at high temperature, contribution is RT and low temperature contribution is 0. Okay. As it is sensitive to temperature. Why? Because the energy associated with vibrational motion it depends on the temperature. That's all. Okay. Now, why the contribution is RT here? Because from the equipartition here question mark you can see you should have one question when I have taught you this one, this R or RT. So now why contribution is RT? Question mark. Why? Why we are saying? Because from the equipartition theorem, what we read about that each DOF consisting of RT by 2 energy. Each DOF consisting of this much energy. Then why we are for one vibrational DOF we are considering RT? Because I have previously told you that vibration is not a single single vibration is not there. For one vibrational degree of freedom there are two vibrations. Okay, so both we have to consider. That's why RT by 2 plus RT by 2 will be there and which results RT because both ways it will happen just for that. So only you have to remember that for translational RT by 2, for rotational also RT by 2, but for vibrational RT, and here one twist is there, at high temperature it will be considered, but at low temperature the contribution will be 0. Fine. Now coming forward, this is the summarization of all the things which you have read till now. This will be helpful for the solving of question. Please look into this in a careful manner. So first, translational degree of freedom, molecular motion, translational motion, degree of freedom is 3. Contribution on contribution to U is RT by 2, we know, and total contribution will be 3 into RT because it is for each DOF and it has 3 translational motion or DOF, so 3 RT by 2. Fine. Again same thing, rotational, for linear it is 2, RT by 2 into 2 RT. For non-linear it is 3 RT by 2 Same for vibrational linear 3n minus 5 RT for each. So RT will be multiplied and it is for 3n minus 6. Fine. So why we are again making a table and seeing these all values? Because it will be now helpful to solve various questions. So for any system, if you want to have the CP value, CP or CP or U, these three, or gamma, these four values actually can be calculated for any system if you are given the atomic uh, atom yes the atoms which consist how much atom is making the molecule. Okay, so n you should know. Okay, so how we can calculate? Step by step manner, you have to follow the steps. Be careful here. Step one is you have to have the idea about what is the n here. So for step one, you should know the n is what is the n. Then for translational 3, if it is if the molecule is linear, it will be the rotational motion part. But if it is non-linear like SO2, this will be the answer for rotational. And for vibrational, you have to consider linear, non-linear also, and high temperature or low temperature. If nothing is mentioned, you can consider the vibrational motion. Fine. So step one is this one. So in the step one, what we get? We get the total contribution. Total contribution means U will be here. From here, U we can write 3RT by 2 translational RT if we are considering that it is linear one. Okay, RT plus 3n minus 5 RT. Okay, and for non-linear it will be 3RT by 2 plus 3RT by 2 again, because it is non-linear rotational part, plus 3n minus 6 into RT. Okay, we know the U. Internal energy part we know. If we know n value, we can put that. Fine, this is fine. Now step 2 is we know du equal to cv dt, right? Du equal to cv dt. So cvm will be du by dt. Okay, so only from this, if we eliminate the t from this equation or this equation, if we eliminate the t, because du by dt will be that only, right? So for every here, in every term, t is only there, t, not t square or 1 by t, only t is there. So in the derivative part, after derivation, it will be just t will be removed. Okay, so we know now the cv we know from here. Here step 3 is cp minus cv minus cv equal to r. So we can calculate cp from here, r plus cv. Fine. The fourth step is the gamma value, cp by cv. So we know now cp and cv, we can calculate the gamma. These 4 steps you have to remember. Okay. Now if we solve some questions, you can understand in a better way. Now something to remember. Value of gamma. Okay, it is actually known that value of gamma is always calculated at low temperature. Means temperature effect is on what? Vibrational motion. So contribution from vibration will be C. Fine. This you have to remember. Okay. I will again in one slide I have made a table for the gamma values for monoatomic, diatomic and triatomic. so that in the question solving portion you have the knowledge about gamma. Now the calculate the gamma value for monoatomic and diatomic molecule. Okay, let's first start with monoatomic. Okay, so monoatomic means n equal to 1. Okay, total degree of freedom. Total DOF will be 3 into 1 is 3. So now first translational trans is always 3, we know x, y and z direction. So 3 is there only, so nothing left. So now rotational contribution will be 0. Vibrational is also 0. Fine. From here contribution will be 3 RT by 2. If we consider the U value equal to U. So we have to find the gamma value. So we have to know the Cp and Cv. So U is this one. That is fine. Because these other things are 0, right? So for your understanding purpose, I am putting all the values. 3 RT by 2 plus 0 into RT by 2 plus RT into 0. Here it is the case. Okay. So U value we got. Now from U value we can calculate Cv. Du by dt equal to only T will be gone. See 3R by 2. Fine. We know now Cv value. So against one box. Okay. Cv value is known. Fine. Now what? Now Cp will be Cv plus R, which will be again 3R by 2, putting the value of Cv R equal to 5R by 2. So now we know the Cp value also. Cp will be 5R by 2. This is clear? Now the gamma value. Gamma value will be Cp by Cv. Cp means 5R by 2 by 3R by 2, which will be 5 by 3. So gamma equal to 5 by 3 is the answer for monoatomic case, which will be approximately, if we calculate 1.66 is the gamma value for monoatomic. Okay, fine. Now for diatomic we have to calculate. You are slowly now understanding the things, right? How to calculate and all. It's very easy. If we understand one time, then you can remember it. Not a difficult thing. So now for diatomic, so n equal to 2. We have to take, right? So n will be here. Total DOS will be 3 into n, right? 3 into 2, 6. Fine. Translational has 3. Rotational, so diatomic means it is linear, obviously. It will be never non-linear, right? So it has 2. And vibrational has 3n minus 5, which will be again equal to 3n is 6 minus 5 equal to 1. But here for gamma, we have previously read that we are not considering the vibration, because for gamma only low temperature values we should have to consider. So vibration will be here not considered. Okay. So contribution will be from here is 3R by 2, and from here it will be 2R by 2. 2 will be cancelled out. So total U equal to will be 3R by 2 plus, sorry, 3RT. Here are 3RT by 2 plus RT, which will be again 2 5R. Okay. So U is there. So now CV will be only R will be removed. Sorry, T will be removed. CV will be 5R by 2. Now CP will be CV plus R, right? So 5R by 2 plus R, which will be again 2 and 7. Okay. So CP value also we know. Now gamma. Gamma will be equal to CP by CV. So 7R by 2 by 5R by 2, which means 7 by 5 will be approximately 1.4. Not approximately, this is 1.4. Okay. So we know now how to calculate for various systems. Now coming to another example, calculate the CP and CV values for triatomic, linear and non-linear molecular in low and high temperature. Okay. So first I will calculate only for high temperature, as high temperature vibrational part is also there, and for low temperature you have to only cancel out the vibrational part. Okay. So first for linear I am calculating, and here total DA will be 3 into 3, obviously 9, translational, rotational and vibration. Okay. 3 rotational, as linear it is 2, and 3n minus 2 means 9 minus, sorry, 3n minus 5 means 9 minus 5, which will be 4. Okay, clear? So from here 3RT by 2, here 2RT by 2 means RT, and from here it will be 4RT, as each vibrational DOF contributing RT. So if we sum these three values, it will be 3RT by 2 plus RT plus 4RT. Okay. Now it will be 2. So 3RT plus 2RT plus 8RT, which will be 30. Please, I am checking if there is any mistake. So 3RT by 2, 3RT by 2, and rotational will be RT only, RT, and here 9 minus 5, right? 3 and 9 and minus 5 will be 4, 4RT, and when this is calculating, this will be 3RT plus 2RT and 8RT. So 13RT by 2 is fine, and CV will be 13R by 2. Okay, and CP will be 13R by 2 plus R, right? Will be 15R by 2. Fine. So these are the answers. So if you are asked the gamma value, you have to, yes, you have to consider the low temperature. So for low temperature, only vibration, this 4RT part will be gone. You can solve it in your pen and paper, in your copy. Okay. Now calculate the CP and CV values for benzene molecule. Okay, I have taken this example because it has some twist. You can be confused here. Okay. So benzene, we know benzene, right? 686. How many molecules are there? 12. Total DOF will be how much? 3N, obviously. 3 into 12, 36. Total DOF. Okay. So now translational 3, obviously. Rotational and vibration. So tell me, rotational will be what? Benzene is this, right? This is benzene, right? So what will be the translational and vibrational part? It is linear or non-linear? Tell me. Why I have said this is tricky? Because it is planar molecule. Fine. But planar is not linear. Linear is like this. One line is there. But it is planar, not linear, right? Because only this one is not there. Na? This side and this side part is left. So this planar, not linear. So it will be considered as non-linear. Here is the twist. So rotational will be 3 and vibrational will be 36 minus 6. So only that part if you miss that for this mistake only CPCV value will be completely changed. Okay. So now we can calculate. Here will be this 3RT by 2 again. It will be again 3RT by 2. It will be 30RT. So you can add and after that you can solve the CP and CV value. Okay, fine. Now one CSIR-NET question is here. In which of the following options the heat capacity doesn't depend on the temperature? Fine. Heat capacity, if you are confused about, so heat capacity, first you will be thinking that CP, is it CP or CV? Because we have read about only these two. Fine. Just forget about the CP. We know that which part we can calculate for if you want to calculate the value of internal energy or gamma, we can calculate from the equipartition theorem. What? CV value. So CV is, we know, du by dt, right? So if you know the CV value, if you know the du value, we can calculate the CV value, right? So now let's consider that CV is only here asked. Okay, because we don't know anything about CP. Just forget about that. So is it temperature dependent? No, right? Because the CV definition only, it was there that for 1 degree change, right? So how then why this question is there? Because we know from equipartition theorem and the degree of freedom when we are reading that we know that for the case of when we are calculating the CV value for the case of vibrational degree of freedom, it was the temperature part was there because it is temperature sensitive. So it depends, not proportional, I will say. It depends. It depends on temperature, right? So if you see here, which of the following options has vibrational degree of freedom in their all the degree of freedoms? then we can say that okay, then if we change the temperature, like if we keep lowering the temperature, so from one point the vibrational degree of freedom will be not considered, and that time CV value will be different, right? Du value will be different and CV value will be different. Okay. So in this options, the monoatomic case, okay, for the monoatomic case, the total DOF is 3, and it is for all were gone for translation motion. So mono will be never the answer. Okay, for diatomic, and also all option is also gone because it is not the correct option. Fine. And for total DOF is 6. Okay. So if right? So is always linear because two atoms like this only. It cannot be non-linear, right? So it will always have 3 translational, 2 rotational, and rest 1. 3 plus 2, 5. 1 will be vibration. But it is always linear. Yes, but it has vibration part in it. So it will be temperature dependent. Temperature dependent, right? So it is temperature dependent. Second option. So it was A, it was B. Okay. C is triatom. Tri. It's obviously dia has the vibrational part. So triatomic case also there will be vibrational part, right? Vibrational DOF. So it is obviously temperature dependent. So we are finding here what? The heat capacity which doesn't depend on temperature. So in the option B and C, vibrational parts are there, which depends on the temperature. So we actually cut down this option, but the question says which doesn't depend on temperature. It will be the mono only. We don't have to consider these all also for answer to solve the answer. Only if we can think about the mono has only translational motion, we can uh, choose the correct option. Okay, so mono will be the answer. Now again one question from CSIR-NET. So in low density, oxygen gas has at low temperature. Low density, we know nothing about this, so low temperature is important. Only the translational and rotational modes of the molecules are excited. Fine. The specific heat per molecule of the gas is specific heat. Okay. Low density and gas is in low temperature. Only in low temperature we know that vibration is not considered, so only translation and rotational modes are there, right? So for oxygen gas, so O2, N will be 2, fine, N will be 2. Okay. Now 2 means total DOF will be 3 into 2, 6. Translational has 3, rotational will be 2, as this is diatomic, and vibration has 1. But here vibration is not considered. So only 3 and 2 will be there. And from here 3R by 2 for specific heat, CV. 3R by 2, and for rotational 2R by 2 means R. Okay. So if we sum it, 3R by 2 plus R will be 5R by 2. So see, we were okay, per molecules means it will be 5K by 2, right? For one molecule. This is for 1 mole. 1 mole. And this is for 1 molecule. Okay. So if you are confused about specific heat is given, but it is not mentioned that it is pressure is constant or volume, means Cp or Cv. But see, after the solving of this question, when we know about the CV value, when we know about the CV value, see, CP will be higher than this value, right? 7 by 2k will be there, but in the option that is not there. So CV value only they want to know. Fine, these kind of questions are also there, which can be tricky to you, or you are confused about what is the question is asked. Maybe it is a wrong question. Let's forget about it and move on. But this very simple question, if you see. So for this question, just uh, do as fast as you can the calculations, and you can know that the option of CP will be not there. Is not here, right? Now some important thing which I talked about, that gamma values for different system. Why I have incorporated it here? Because you can calculate it, right? But for some general, because for benzene you can never remember that value, right? But for monoatomic, diatomic and triatomic, these three, mainly the mono and dia, you should remember, because for to solve question in a faster way, the value will be helpful, very helpful. Because if you, some adiabatic question is there, like I'll be solving one question from that in the next slide. But let's say for any adiabatic work equation or something like that is needed, right? So for that, gamma value you should know, because in the work expression only gamma value is there. If you solve first gamma value and then come to work value, that will be very time taking. Okay. So my advice is these few values you have to remember. Okay. Now coming to the next question. So it is asked in CSIR-NET June 2020. So it is recently asked. Monoatomic gas, right, undergo expansion from P1 P1 to P2 V2 under isothermal or adiabatic condition. Okay. The pressure of the gas will fall more rapidly under adiabatic conditions, because, so we know for the adiabatic condition the graph is like the slope is high, so fall is faster, and for the reversible isothermal case, the fall is slower. Means the slope is not as much high as adiabatic. Right? This is PV graph. So this is obvious, but they want to know that which equations this adiabatic process is following. We know for adiabatic process, P v to the power gamma equal to constant is there, right? Means, which we can write from here, P is proportional to 1 by v to the power gamma, because to equalize we have the constant value, but if we don't want to equalize, then 1 by v to the power gamma term is there. Fine, so we should know the gamma value. So now monoatomic perfect gas is given. So for monoatomic gas, you know that gamma will be 1.66, or let's say if we calculate it, monoatomic case, it is simple. Only 3R by 2 is there, right? CV, and CP will be 5R by 2. So gamma will be, this is CP and this is CV. So gamma will be 5 by 3, right? So the equation will be now area size 1 by p to the power 5 by 3. Fine. So answer will be this one. Simple. But seeing the question, actually you can be confused that a very tough equation is there. What is to the power 7 by 7 by 5 to the power 7 by 3 by 2, etc. You can be think about, right? So you should not actually fear, have fear to solve the question. By seeing the question, you have to first underline. In the online manner, you cannot underline the question, I know, but in your mind, you should remember this, the main important points. that here, let's say in this question, monoatomic perfect gas is given, right? And expansion is the important thing, right? So from expansion we can write V2 greater than V1. So this kind of, in short note, in the pad itself you can write this kind of short note, so that you maybe forget about something, that expansion is given, or the compression or something like that. You can be confused after solving the question, and the mistake can be there. So to make a short note about the quick note about the question is sometimes helpful for this kind of, let's say, bigger question. Okay. So monoatomic gas, expansion, and isothermal process is also there, and radium, right? These simple words you have to choose from these three lines. Then you can obviously solve the question. Okay. So today I will talk about till now, because you have today you have I have introduced some various important things to you. So you practice well, and I'll be again here with a new topic, new interesting and obviously helpful topic for you. Okay. So till then, bye.